My name is Ryan Thompson, and this is my CPSC5210 complexity exercise assignment. We had several exercises to complete. Hard to do these video submissions explaining exercises. So on my screen now, you'll see the exercises, and I will explain my steps that I use to arrive at the answers for each of the exercises. The first exercise we have is asking us to that the upper bound is equal n squared, and it's given us the total time formula, and it's asking us to, by proving this statement, is we use substitution to prove it by taking in, and we know that because big O is the upper bound, T of n in the worst case can only be low. So following the substitution practice, you substitute T of n, that's what you have here, and then plus n. And so this is the basic method for substitution. So in the future, and just start at the statement. Once we expand the terms, we have here C be any factor. So I'm going to let C be 1. Be 1 leaves us with n squared minus 2n plus 1 plus n. Reducing the terms, you have n squared plus 1. Now, because n squared minus any factor here, as long as that factor will be less than n squared itself. True for C is equal to 1 and n is greater than 1. From here, we've proved that given this total time, there is the upper bound, big O, n squared. This by the master theorem, which is another way that we can check and add a final definition. So here's our basic formulation, is that T of n, if n is equal to 1. And here's the function T of n divided by b. So this is the time for each node, and this is the number of subnodes. So the time for the node, subnodes, plus the runtime to actually solve the recurrence. Well, the bi, where a is greater than or equal to 1, b is greater than 1, and I is a positive real number, or the natural numbers. So 1 up to positive infinity by integers only. Well, here following this form, above b here, because it's n divided by b, b would be equal to 1. And here again, I, or n, is greater than or equal to 1. So those two basics are satisfied, but because b must be greater than 1, 1 is not greater than 1, so it's not valid, and this problem is not solvable by the master theorem. So that concludes exercise where you're just asked to validate that big O n squared is an upper bound for this function. 4.51b and problem 4.1f are the same problem, so for the purposes of saving time, will explain it the one time. So we have this form, this runtime. Of n is equal to n divided by 4 plus the root of n. You're asked initially like upper bound, or the aspect in tight lower as best you can for the master theorem. So we'll go ahead and go straight on to the master theorem. Again, the functional form T of n 1 if n is equal to 1, and the form AT n divided by b plus f of n if n is equal to b I, where I is equal, or an element of the. So in this form, again, a is equal to 2, b is equal to 4, f of n is equal to the square root of n. And again, we have to validate the assumption. So a is greater than or equal to 1, that works. b greater than 1. That works. And I is, again, falls in natural number. So this holds for the lemma 4.4 in the book. So what we're trying to prove now is that f of n is equal to theta n, or theta of n log b, which was 4, 2. So that gives us n to the square root, which both are equal to. Then case 2 applies in this, following this recipe, this cookbook. So t of n is equal to theta n log b to the a, so 4 to the 2, log base 2 n, which gives us theta square root of n log n. Now that gives us our asymptotically type upper and lower bounds. So I just wanted to try and work this out by substitution to see if if there is a functional form that you can get n log n. So again, working in the substitution, t of n, 2, c n divided by 4, log n divided by 4 plus d plus square root of n. So this functional form here comes from this theta over here, because we're doing substitution. So t of n substituted in theta n over here. So expanding out the terms, c n to the log n divided by 4 plus 2d. Working out the math continually, or expanding out this log term to get rid of the fraction. C log n minus c to the n 1/2 2 plus 2d plus n squared. Again, letting c be a number of our choosing. The c just disappears. It really has no influence at the value 1. So n of 1/2 log n minus 2n plus 2d plus n squared. So now I actually worked this problem out before and arrived at a problem where I couldn't get some of the terms to cancel out and I couldn't get them to work down to n log n. So following the book suggestion of subtracting a term when you know that you have the right bounds is valid. And we know that we have the right bound because we used the master theorem. Adding in d, you can let d be 1/2 n, and this allows the terms to cancel here. So 2d multiply 1/2 leaves you square root of n. So square root of n plus square root of n is 2 square root of n. Now you're left with square root of n for c is equal to 1 and d is equal to 1/2. So you've proved that given these two parameters, that this is a bound for square root of n log n. So without loss of generality, I added the lower order term. Now what if I subtracted the lower order term? So if d is subtracted, then d takes on the form, because everything else is constant through here, and negative. So instead of d being positive 1/2 times square root of n, it'd be negative square root of n. Therefore, theta is valid as the asymptotically tight bound for c is equal to 1 or d is equal to plus or minus 1/2 square root of n. So again, this is for exercise 4.51b and problem 1.1f. So on problem 4.1a, we have another runtime to evaluate and give a tight asymptotically upper bound, or asymptotically tight bound. So t of n is equal to 2 t n divided by 2 plus n to the 4. So again, this is the form that we have to evaluate every time for the master theorem. Ask if these conditions hold. If they do hold, then we can proceed on. If not, it can just simply plausible or not by the master theorem. So theta of 1 if n is equal to 1, a t plus f of n if n is equal to b sub b raised to the I. If a is greater than or equal to 1, b greater than 1, and I is element of n. So since here, following this form, a is 2, 2 is equal to a, which is still greater than or equal to 1, and b is also 2, so 2 is equal to b greater than 1. Here, 1 is equal to I, element of the natural. So this is solvable by the master theorem. And I think the book also points out that merge sort, this is the basic for merge sort. So this looks pretty similar to most of us from the example. So here, f of n takes on n is equal to, f of n is equal to n raised to the fourth. Theta is this basic form that you always have to evaluate, and that's n log b a. So log base 2 raised times 2, that gives you 1. But for f of n to equal theta, there must exist some epsilon greater than 0. So f of n, you can, in this case, the math is very simple to see that for f of n to equal theta, n log b of a plus some epsilon is n to the fourth. And that's theta n log 2 to 2 plus 3 is equal to n to the 4. And here's that ratio verified again, because it must be polynomial larger. Epsilon must be polynomial larger, bounded to work, because epsilon cannot equal 0. So if you have a case where epsilon must equal 0, then it can't work. The form can't be solved, and it actually falls into buckets between case 2 or 3 or 1 and 2, and there's another form for that to be solved. So here, just to review on how you can come up with this 3, or how it can be used in other cases. So f of n, the recursion, over this form for theta, that's n to the 4 of n log 2 to 2. So n4 over n1, that leaves you with n3. And so based on the statement in the book, or the theorems in the book, as long as n raised to the epsilon such that epsilon is greater than 0, polynomial larger, therefore epsilon is equal to 3. So again, that's how the 3 got into there. And this falls into case 3 because you're adding, so you're finding omega, which is your up or your lower bound. F of nb is less than c f of n. So this is the last condition that you need to validate in sufficiently large n. So 2 of fn divided by b to the fourth less than c n to the fourth. Continue on the math. That's 2 over 2 raised to the fourth into the fourth is less than c into the fourth. 1 over 2 cubed, or 1 over 8 into the fourth, less than c into the fourth. And now if you divide into the fourth on both sides, thirds less than equal to c. That's clear from the math. But again, the statement of 1 over c can be between those two bounds. Therefore, case 3 does hold. T of n, the total runtime, is equal to theta f of n, which is equal to the fourth. Another problem asked to solve to give the asymptotically type bounds is t to the n is equal to 7t to the n divided by 3 plus n squared. So again, evaluating the form, t of n, or the conditions, t of n, where theta is 1 if n is equal to 1, and t of n of a, t, n divided by b, then if n is equal to b. Right? So again, the number of subnodes, the number of time per node, and the recurrence at each node. So if a is greater than or equal to 1, if b is greater than 1, it's I is an element of the natural numbers. And you can see here, 7 is equal to a, greater than 1, that works. 3 is equal to b, greater than 1, that works. And again, sorry, a needs to be greater or equal to 1. And 1 raised to the I is element of n, thus this is solvable by the master theorem. So that's just our starting point. So these conditions, now f of n is equal to n squared, which is up here, again designated by the form. So theta n log b of a is equal to n log base 3 to 7. And following the ratio procedure as outlined here of f of n over n log b, we can come up with the bound that 1 log 3 to 7, which is less than 2, And since we're trying to get to n squared, we know that log 3 to 7 is between these numbers, so there's some epsilon that we need to find. So epsilon needs to reach 2, and we know log 3 to 7 is greater than 1, but less than 2, which we have here. So epsilon is equal to this differential, or this difference, not differential, is equal to this difference. Then case 3 applies, because again, we're adding a term, so that's the omega, or that's the lower bound. So if condition case 3, that's a f of n divided by b is less than c f of n, then c it for c less than 1 and n sufficiently large, f of n divided by b squared is less than or equal c n squared. And again, carry out the math. 7 divided by n is less than, or 7/9 is less than or equal to c, which is less than or equal to 1, which is part of the original statement. Therefore, t of n is theta f of n, which is theta n squared. So again, c is less than 1, but greater than 7/9. So again, this bound is valid. And here's the last problem statement. So t of n is equal to 4t. So this is the first time that we've seen a f of n that's not some standard form of n raised to a polynomial that we're used to seeing in all these cases. You can see here that's n to the 1/2, so it's some type of polynomial that we're used to. I had thought that this would not hold, but what I did not do is check the ratio before. I saw that there's another statement that's close to it, like if you had the merge sort divide of 2t n divided by 2, you wind up with a polynomial that you can't solve because there's no polynomials left. So, but that's not this case. So t of n is theta 1 if n is equal to 1, or a t of n divided by b plus f of n if n is equal to b raised I. A is greater than equal to b is greater than 1. It's an element of the natural numbers. Well, since, again, following the form, a is equal to 4, b is equal to 3, and it's still greater than 1, so we're on the right track, and 1 is equal to I, element natural. So now this condition holds so that we can go further with the master theorem. So f of n, again here, deriving from here, theta n log b of a, this is our standard form that you're always going to evaluate it against, is equal to n log 3 to the 4. So now we're going to check the ratio to see if it's asymptotically bounded. Log 3, 4, there's some polynomial is bounded by. So n is less than n log 3 to the 4. So there exists, so trying to save a little space, there exists the epsilon greater than 0. N is equal to n log 3 to the 4 minus epsilon. So this is the first time that we're seeing the case 1 appear. So we're seeing big O come back for 0 is less than epsilon, but that's less than log 3 to the 4 minus 1. So we know trying to get into the power, and we know log 3 to the 4 is greater than 1. So this epsilon may not be very large, but it is greater than 0. That's the condition for, because you're subtracting an epsilon out. So case 1 applies, and there's no other. You don't have to do this functional verification like you do case 3. So case 1 applies, therefore t of n is equal to theta n log b to a, which is equal to theta n log 3 to 4. So that covers, we've seen a case 1 apply, case 3 is apply, and always knowing that we still have to continually evaluate this statement. Book has another problem that says this is an overspecification, but continue to evaluate it anyways. That shows that C is bounded. And we've shown two different ways that you can use substitution or the master theorem to get at these upper bounds. And that is my homework and all my explanations for this problem set. Thank you.